Okay, so this is homework 6, problem 2. And so we're given that x and y are two independent and identically distributed random variables with a common PDF. So as we can see, the marginal density function of x and the marginal density function of y are both exponential density functions. And they're both multiplied by the unit step function, so they're all positive. And so, in order to find x plus y, since x and y are independent, we can simply just do the convolution for continuous random variables. And so the formula for convolution of continuous random variables is equal to fz of z is equal to negative infinity to infinity of f of x times f of y of z minus x. So how do we get z minus x? So since z is equal to x plus y, then we have to substitute in z and y for x for f of y. So y in terms of z and x is just equal to, so we can just move the x to the other side, and it'll be y is equal to z minus x. So we substitute in z minus x for all y's. And so we get 0 to z because the function is always positive because both of the x and y are multiplied by the unit step function. So those values are strictly all positive. So the minimum is 0. And at the greatest, z, because it's x plus y, which is equal to z. So it's from 0 to z of e to the negative x times e to the negative y, but we substitute in z minus x for y. So it's negative z minus x times dx. And so when we integrate, when we multiply that out, the e to the negative x's cancel out, so it's just e to the negative z. So it's e to the negative z of 0 to z, which is equal to e to the negative z 0 to z dx. I forgot to write a dx in there. So since it's in terms of dx, we get z e to the negative z. And that is what x plus y is equal to. Similarly, for x minus y, it's the convolution of two independent continuous variables. And so, since z is equal to x minus y this time, y is equal to x minus z. Instead of z minus x, it's x minus z, because x minus y is equal to z. And so it's from 0 to z, for the same reasons as before, of e to the negative x times e to the negative y, which now is x minus z, so it's e to the negative x minus z dx. And so when we break that apart and we multiply the two e's with each other, we get e to the negative 2x times e to the negative z dx. Which further substitutes, since it's in terms of dx, e to the negative z can be pulled out of the integral. So it's the integral of e to the negative 2x of 0 to z, which ends up equaling e to the z times negative e to the negative 2x divided by 2 plus 1/2. And after messing around with the equation, we can see that the 1/2 can be pulled out. And when you multiply e to the z with all the two terms, you get e to the z minus e to the negative z. Okay. And so for part B, part C, we're asked to find what would be the product of these two identical and independent random variables. So since these are both exponential. And so we're asked for the product. And so this is the graph of what z would look like. So for when the functions of x and y become more complicated, it would help a lot to plot down what z would look like. So z would look like this, and we're trying to find the area under this curve right here. And so we know that x is strictly positive and y is strictly positive because both x and y are multiplied by the unit step function. And therefore, z is also strictly positive. And so in order to do this, we first have to find the area under this curve. So the area under this curve under a density function will result in the mass function. So we'll get big F of z. So big F of z would be big F of z times, so we'll find big F of z times x to y. So we get times e to negative x times e to negative y. Over the bounds. So as you can see here, the bounds of y, for instance, go from 0 to this graph here in terms of x and z. So if you want to get that, you would just have y is equal to the x will go to the other side. So it's x equal to z divided by x. So that's the bounds of y. And the bounds of x would simply just go from 0 to infinity. Okay, so now we can do this. In the next part, since we're integrating with respect to y, e to the negative x can come out. So it'll be e to the x, negative x, times the integral from 0 to z divided by x of e to the negative y. And that gives us 1 minus e to the negative z divided by x when you do the integration. So this can be multiplied out. So the first part gives you e to the negative x from 0 to infinity, plus negative e to the negative x plus negative x minus z to the z over x from 0 to infinity. And so we know that this integrates into negative e to the negative x from 0 to infinity, but we know that that ends up equaling 1. And we can just simply move this integral down. We don't have to integrate this. In fact, it's actually incredibly hard to integrate this. But the trick of this is that we don't actually have to. So we know this is big f of z. In order to get small f of z, it's just simply just the derivative of big f of z. So we can take the derivative of this entire term here. So we know the derivative of 1 in terms of z is going to be equal to 0. So that goes away entirely. And then the derivative of this with respect to z becomes just simply negative 1 over x, because x just becomes a constant when it's in terms of z. And this goes to 0 because it's just like a constant. So this constant, the derivative of constants is just equal to 0. And then this is just negative z over x, so the derivative of that is equal to negative 1 over x. So that can go in front, just like here. So the negatives cancel each other out, and ultimately we just get small f of z is equal to 0 to infinity of 1 over x times e to the negative x minus 2 divided by x, z divided by x dx. And this is for z positive. So another way of writing this, you can simply just write this entire function times the unit step function of z, which will give you basically the same thing as saying for z is greater than 0 or equal to 0. In order to find the quotient of two random variables, it would help also to plot again. And so we know that z is equal to x over y, and therefore y is equal to x divided by z, which looks like this line here, and you want everything above that line there, because you want y to be greater than x divided by z, because z has to be strictly positive, and y is strictly positive. So we get, just like we had before, we have the area over this entire region gives us the mass function. In order to get the density function, we do the derivative of this function. And so it's going to be the integral over the product, of these two functions from the range of these two functions. So the range of x goes from 0 to zy. So how do we get that? So if we have z is equal to x over y, then x is simply just equal to z times x. You just multiply the y across. So that's the range of x in terms of z and y. And then dy simply just go from 0 to infinity. So you can see from here, x goes from this 0 here to the graph here, and then y simply just goes from 0 to infinity. And so when we integrate it out, since we integrate with respect to x first this time, e to the negative y can simply just come out, and it'll be the integral of e to the negative x from 0 to zy. And so that ends up equaling 1 minus e to the negative zy. And so similarly, the first part, e to the negative y from 0 to infinity, this just becomes 1. And then this integral, this time this is integratable. So the integral of 0 to infinity of e to the negative y, negative e to the negative y minus z times y dy. So since we're doing integral with respect to y, we have to use chain rule for this. And so this will take the derivative of this and the derivative of the second term. The derivative of the first term is just negative 1. The derivative of the second term with respect to y is negative z. So that comes out on the bottom, because when you take the derivative of this cancels out and you get what you started off with. Okay, so since you can pull that out, it's e to the negative y minus zy of 0 to infinity. And at infinity, that term becomes that term becomes 0 because it's 1 over an incredibly large number. And at 0, it becomes 1 because e to the 0 becomes 1. And so we get big f of z is equal to 1 minus 1 over 1 plus z. And so the density function of z is equal to the derivative of the mass function of z. So the derivative of 1 goes to 0, and the derivative of negative 1 over 1 plus z is equal to 1 over 1 plus z squared. For z is greater than 0, or like I said before, since you can represent z is greater than 0 by the unit step function of z, by multiplying the unit step function of z, this is also a valid alternative to the answer. And that is number 2.